A single next-generation NVIDIA H100 GPU generates a massive 700 watts of thermal design power when operating at peak capacity. Standard enterprise server racks are engineered to cool 2 to 10 kilowatts. A single high-end AI server running 8 GPUs pulls up to 15 kilowatts on its own, exceeding the physical cooling capacity of traditional data center architectures. In many boardrooms, this transition is still debated through the binary lens of choosing between an all-cloud or all-on-premises deployment. This binary approach fails to account for the intersecting constraints of thermodynamics, data sovereignty, and capital efficiency that define GPU workloads. To manage this, architects adopt a 4-tier framework. First, owned hardware, enterprise on-premises for localized security, and AIDCs for high-density power. Second, rented hardware, Telecom GPU Clouds for regional agility, and public compute for massive global burst traffic. Workloads are routed across these tiers based on task topology, financial utilization, and physical grid limits. Deploying enterprise AI requires solving for these physical and financial routing variables, moving far beyond the scope of a standard IT procurement decision. Task topology dictates the first routing constraint, the physical distance between the compute hardware, the data source, and the end user. This distance map separates the control plane from the data plane. The 1 to 10 millisecond edge ring supports air-gapped on-premise tasks. Telecom clouds handle the 10 to 50 millisecond regional gap for sensitive queries, while public compute absorbs 150 millisecond WAN latency for global burst traffic. Real-time alerts stay on-premise. Document retrieval fits telecom clouds. Massive training needs public compute. Data gravity and network jitter disqualify the public cloud for mission-critical near-edge AI execution. The second constraint is the financial threshold of hardware utilization. Hardware utilization percentage drives total cost of ownership, making cloud OpEx expensive at scale. For experimental or low utilization workloads, those running under 50% of the time, renting compute via telecom or public clouds protects capital. However, stable production workloads require analyzing the costs of a standard 8 GPU pod. This chart shows the monthly GPU hour break-even points for operating a single 8 GPU pod, comparing ownership costs in a private facility versus an AIDC over a 36-month lifecycle. The financial advantage shifts at this intersection, the golden cross, reached at 52 to 60% utilization, roughly 3,000 to 3,800 hours monthly. At 70% utilization, owning AIDC hardware drops per GPU costs significantly below public cloud rates. Stable AI production makes rented compute a substantial financial liability. The final constraint involves the physical limits of power and government grid regulations. This scale shows power demand rising from standard IT racks at 10 kilowatts to next-generation AI clusters that redline at 250 kilowatts per rack. Passing 50 kilowatts hits the thermal wall, where air cooling no longer has the thermal capacity to dissipate heat. Advanced liquid cooling, whether implemented as direct-to-chip solutions or full immersion tanks, has become a strict engineering prerequisite for modern high-density enterprise AI deployment. These thermodynamic requirements shift the focus to external grid regulations and finite regional power capacity. Taiwan has restricted new data centers over 5 megawatts in its northern region, forcing new infrastructure to migrate southward to find available power. State mandates also require these high-density facilities to maintain a power usage effectiveness, or PUE, of 1.3 or lower to operate. These thermal and regulatory requirements prevent enterprises from retrofitting standard office buildings to house AI clusters. The specialized AI data center is the mandatory physical vessel for high-density compute, bridging the gap between hardware savings and local grid limits. Enterprise architects must build a dynamic routing protocol for AI workloads instead of defaulting to a single fixed platform. This decision engine filters workloads through 3 specific gateways: data sensitivity, utilization percentage, and physical capacity. Rule 1. Unstable demand or testing phases should route to telecom or public clouds to prioritize OpEx flexibility. Rule 2. Stable demand above 60% that requires liquid cooling should route to a specialized AIDC. Rule 3. Hypersensitive data requiring low-density, air-cooled compute should route to an enterprise on-premise facility. Aligning latency needs, utilization rates, and physical grid constraints ensures long-term operational resilience. Success relies on mastering the physics, economics, and topology of the hybrid compute matrix, far more than simply selecting a cloud provider.